Good day! My name is Rainier Joseph B. Talite, and today I'll be presenting Homework 1 on the Myhill-Nerode Theorem under Automata Theory and Formal Language. We'll analyze the simple language, determine its regularity, and walk through the process step by step. Let's now proceed to our language definition. The given language is L sub 0, which contains only 4 strings, the empty string epsilon, the string A, AA, and AAA. Our alphabet is sigma is equals to A, and our task is to determine whether this language is regular using the Myhill-Nerode Theorem. But before we start, let's review the Myhill-Nerode Theorem. It states that a language is regular if and only if there are finitely many equivalence classes under relation. Two strings x and y are equivalent if for every string z, xz, and yz are either both in or both not in the language, meaning they can't be distinguished by the language. The following visual representations illustrate the Myhill-Nerode theorem applied to our given language L sub 0 to determine if it's regular. This portion shows the conceptual view of equivalence classes within sigma star, which is all possible strings of A's. We have 5 distinct classes. These classes group strings that behave identically when any suffix is appended. We have 5 states, each representing an equivalence class. States Q0 to Q3 are accepting since the empty string A, AA, and AAA are in L sub 0. Q4 rejects all strings of length 4 or more. Each A moves to the next state with Q4 looping on itself for longer strings. And this one illustrates string distinguishability. In the left box, we have AA and AAA are distinguishable because adding suffix A produces AAA, which is in L sub 0, and A to the 4th, which is not in L sub 0. In the right box, we have A to the 4th and A to the 5th are indistinguishable because for any suffix Z, both A to the 4th concatenated with Z and A to the 5th concatenated with Z will be rejected. We now consider strings from sigma star, which are all combinations of A, including the empty set, A, AA, AAA, and even A to the 4th. Even though A to the 4th is not in the language, we'll include it to test how strings behave when extended. This helps us build equivalence classes. Let's now check if pairs of strings are distinguishable with respect to our language. In the first row, we're comparing the empty string with the string A. We test both by appending the suffix AAA, which is empty string plus AAA is equals to AAA, which is in the language L sub 0. Then A plus AAA is equal to A to the 4th, which is not in L sub 0. Since one result is in the language and the other is not, they are distinguishable. Now, in row 2, we compare A and AA, and we use the suffix AA. A plus AA is equals to AAA, which is in L sub 0, and AA plus AA is equal to A to the 4th, which is not in L sub 0. Again, because the outcomes differ, A and AA are distinguishable. Row 3 compares AA plus AAA, and we test them by using the suffix A. These strings produce different results, so they are distinguishable too. Next, row 4 compares AAA and A to the 4th with the empty suffix, so one results to an output which is in L sub 0, and the other which is not in L sub 0. Once again, different outcomes mean they are distinguishable. Finally, in row 5, we compare A to the 4th and A to the 5th using the empty string as the suffix. Both outputs are not in L sub 0. Then, they are not distinguishable. Now, we summarize our results. One equivalence class includes all strings in the language, which is the empty string A, AA, and AAA, and another class includes all strings not in the language, like A to the 4th, A to the 5th, and so on. And since we found a finite number of equivalence classes, specifically 2, by the Myhill-Nerode theorem, we can confidently conclude that the language L sub 0 is regular. That concludes my homework 1 for finals. Thank you for listening. I hope this helped you understand how to apply Myhill-Nerode theorem to a finite language. Have a great day!